happen in the banquet hall post-lunch. So post-lunch, we'll have a 2-track conference. And finally, if you have any questions, comments, do tweet out to us. Our Twitter handle is @JSFoo. The hashtag is #JSFoo. So we hope you enjoy the conference today as much as yesterday. We have a bunch of talks happening today, starting with a very interesting talk on data visualization and handling it in browser, and then a talk on Elm, and a whole bunch of talks, including an Angular talk. So whoever thinks it's a React conference, not a React conference.
Hello. 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 Feedback. Thank you. Should I start? Okay. Hello.
Please put your phones on silent. Thank you very much.
So hi, everyone. My name's Curran, and I'm going to talk about data visualization in the browser today. So the purpose of this talk is twofold. I want to give you a technical introduction to the techniques for data visualization in the browser, including D3 and SVG. And the second purpose of this talk is to give you a sense of what's possible with these things. So this is the tech stack that I use and that I'll be talking about today. It's purely on the front end, nothing on the back end. And CSS, HTML, and JavaScript. And SVG is what I work with for graphics. I'm just curious, how many people have worked with SVG? Oh, great. Great. And everything I'll show will be using D3, data-driven documents, a great JavaScript library for graphics. Who here has worked with D3? Cool, about half. Nice. So I want to point out that my slides are available. If you go to Curran Kelleher, no space, twitter.com/Curran Kelleher. The link is there if you want to follow along. Something happened there. So I'll begin with the technical part to get you sort of familiarized with D3, if you're not already in graphics. So these are a bunch of rectangles on the screen. It's kind of a pseudo bar chart. It's not really a bar chart, but it's the essential essence of a bar chart, right? And so, first of all, SVG stands for Scalable Vector Graphics, and it's as opposed to raster graphics. When you use image files, it's raster graphics, meaning each pixel is defined in the image. But vector graphics is different because SVG defines the shapes, the coordinates, and the shapes. So you can zoom in infinitely, and you won't lose any resolution. That's the idea of SVG. So here's the code for that pseudo bar chart, just as SVG. So this is basic usage of SVG with no JavaScript. It's an HTML page with an SVG element that has a width and a height, and 4 rectangles, each of which has x, y, width, and height specified in pixels. And if you're not aware, in this coordinate system, y equals 0 is at the top of the screen, not the bottom, which is opposite from math. So here's the second iteration of this pseudo bar chart, and this code uses D3, just to give you a sense of the structure of the D3 patterns. So I've encoded the data as x, y, and height for each of these bars, because that's what varies between the bars. And then this is the typical D3 pattern for making these SVG elements from data. So the SVG element is there already, and we're selecting it with D3, and that gives us a D3 selection. And then this is the data binding part of D3, where you select all rectangles, and there are no rectangles at this point. And then you bind it to this data, this array of data. And then you get this enter virtual selection, which corresponds to the data that doesn't have any DOM elements corresponding to it yet. And then for that virtual selection, you append a rectangle for each element of this array. And by the way, this is usually how data is structured in memory when you use it with D3. It's an array of objects. So if you think about it as a spreadsheet or a table, each object is a row in your table. And then this is how you can use these functional programming kind of patterns with D3 to set these attributes of the DOM elements. So it constructs the exact same DOM as we saw before, but now it's driven by data. So you can pass in a function of D, and D is just a convention. This is for each row. Each row of the table will be D here. So it just returns D.x, D.y. And you can also give it a constant value, like 170, because all the widths are the same for these rectangles. And then sort of a third iteration of this pseudo bar chart uses data instead of data that has x, y, because x and y, that's the language of pixels, right, in graphics. Usually data doesn't have that. So you need to use D3 scales to map the data to the graphics. And this is what D3 scales are all about. So let's say you have a table with different names and different values, 5, 4, 3, 2, 1. You can use D3 scales to map those data values to pixel values. And I don't think I'll cover this in full detail, but just to give you a sense, this is sort of how D3 works. You have an array of objects. You use scales to map them from data space to pixel space, and then you use this update pattern of D3 to generate these DOM elements. And then a fourth iteration shows how you can load it from a CSV file. So here's an asynchronous call that loads data.csv. And this is the content of data.csv, which gets loaded and transformed into that array data structure that you saw earlier. So that's the technical introduction to D3 and how you can generally work with D3. So from here on out, I'm not going to go too detailed into the code, but I'll just show you different examples of what you can do with D3 once you get familiar with it. So the idea here, and this is why I love data visualization and graphics, the idea here is that data visualization, in my view, is kind of like a telescope that you can point at the universe of data that's out there, that exists, or it's in your databases. And what you're really pointing it at is this digital mirror of the world. Things happen in the world, and then data gets recorded about those events that happen. And this digital mirror world is getting constructed all the time. And I see data visualization as a way to look into that universe, so you can understand the world better by visualizing the data about the world. So let's give some meaning to these bars. So here's a bar chart that shows the top 5 countries, the largest 5 countries in the world. So you can see it's India, China, US, Indonesia, and Brazil. So I remember the first time I saw this graph, I was shocked to see how much bigger India and China are than all the rest of the countries in the world. And you don't get that kind of perspective if you look at numbers. You get that perspective if you see graphics. And with your eyes, you can see, they're actually a lot bigger. And you don't get that perception with just numbers. So another thing that I was curious about is religion. What are all the religions of the world and how are they distributed? How do they break down? So here's another bar chart. It's a variation of a bar chart that's horizontal. And horizontal bar charts are great because you can show many more bars. And so this is some data from the Pew Foundation about different religions in 2010. It's an estimate. So I was also kind of shocked when I saw this for the first time. I didn't realize that there were so few Jews in the world. Can you imagine that? See how small that slice is? And the majority are, well, I don't know about the majority, but the largest population of religion adherents are Christians, Muslims, and unaffiliated. Unaffiliated is number 3. Can you imagine that? And then Hindus is number 4. And can you guess where all the Hindus are? So this next chart sort of breaks down the chart one level further, and it's a stacked bar chart. It's a horizontal stacked bar chart. So this shows you the religious breakdown of the largest 20 countries. So you can see the Hindu segment is red here, and you see they're all in India, almost all. And there's some in Bangladesh as well. So I'll go through the code real quick for these charts as well. It's similar to what we saw before. We're loading from a CSV file this data about the countries, and then we're rendering it using D3 scales. And D3 has axes built in. So that's one fantastic thing about D3. The axes are these tick marks up here, 1.2 billion, 1 billion, China, India, US. Those are from the D3 axis module. And the way that D3 axis works is you create an SVG group element. And SVG groups are great for grouping elements together. You can translate a bunch of elements at the same time if you put them in the same group. And then you call the axis with the SVG group element, and it will render this axis kind of magically. So here's the interactive version of this stacked bar chart of religions, and I want to kind of show you interactions that you can add to any visualization. One of the most common interactions is tooltips. It means when you hover over a certain shape, you get more detailed information about that shape. Like this rectangle represents Christians in Mexico. There are 107 million Christians in Mexico. And you can hover over any of these bars and see these numbers. So if you go back to the telescope analogy, visualization is a telescope into the universe of data. You could think of this visualization type, a stacked bar chart, as kind of a lens that you can put on this telescope, and you can point it at anything, So if you have databases of your application's data, how many customers are buying which products at which time, you could apply this lens to that data as well, and then visualize it, and then you perceive the data more clearly than you do if you just see numbers in tables. Another interaction here is you can hover over the color legend, and it will highlight just the matching bars in the bar chart. So this is useful if you want to ask the question, well, where are all the Hindus in the top 20 countries? You can just hover, and it will highlight them. And without that highlighting, it's sort of hard to see that there are Hindus in Indonesia, United States, and Pakistan. But you can see it if you sort of fade all the other ones to the background. And you can see the majority of Buddhists are in China, and Japan, and Thailand. And there's a small segment in India. So going back to this telescope analogy too, you can sort of zoom into one part of the world and say, what does it look like around here? So this visualization is just essentially a scatter plot, meaning there are circles, and each circle corresponds to a city. And there's zooming here. That's another common interaction in visualization, is zooming. You can apply zooming to most visualization types. So you could zoom out, and it's just circles. And you still get a sense of the world. You get a sense of the world map here. And you can zoom in to India, and again, there's tooltips on hover. And by the way, this is outdated data, so don't take it literally. I think it's from 2005, maybe. So it says Bangalore, there's 5 million people. But if you zoom in here, you can kind of see, okay, Bangalore is a huge city in this region. But what's this other circle? Oh, it's Chennai. And then, you know, you can sort of navigate around and say, oh, there's a huge city over there. What's that? What is it, guys? Mumbai, right? And you can see, yeah, the tooltips, 12 million in Mumbai. And there's a bunch of smaller cities around Mumbai. It's a huge metropolitan area. But in terms of the code, this visualization is actually very, you know, I would consider it simple. It just loads the CSV file. Each row is a city that has latitude, longitude, and the population. And it just maps each city to circles with this code here. You know, it's SVG still. Make a circle for each city, and then just use the scales. And you can see how the scales are set up. The radius corresponds to the population. And by the way, if you use circles in visualizations and you size them by some data, you should use a square root scale, not a linear scale, and it should start at 0. If you do it that way, then the area of the circle corresponds to the data. But if you use a different kind of scale, like a linear scale or a log scale, then the area of the circle doesn't correspond to the data anymore. It kind of skews how you perceive it. And this is a style I like to use where I use variables for the columns. So in a lot of D3 examples, you see the columns are hard-coded in the visualization code, but you can extract them as one step toward making reusable visualization components. So you can see up here I have these variables, you know, X column is longitude, Y column is latitude, and the R radius column is population. But this is a fairly rough view of the world, right? You just get the cities, but it still gives you a sense of where the people are. I think a better proxy for where people are is this awesome data set from NASA, the Earth at night. And this is what that data looks like, overlaid with labels. And this is using D3 as well, using a module called D3 Tile that lets you make tile-based maps. So now you can see much more detail about where the people are on the surface of the Earth. And so this is the light coming out of the Earth at night, picked up by NASA satellites, and then they've released it as public data. But if you just look at the NASA data, you can't match up the bright spots with the city names. So I use D3 to add another map tile provider that gives you labels and put that as a layer on top. So here's the interactive version. There's zooming here as well. So you can see the labels load separately from the background map. You can see Bangalore is a big area, Chennai, Hyderabad, you know, Mumbai and Pune, they're right there. There's a lot of people there. And then if you look at northern India, I think this is fascinating. See all this density of people up here? Jaipur, New Delhi, and all this huge population density up there. And I think it's just fascinating to look at this. You can see how people are distributed. And when I first made this, I zoomed into the US. And then I made it so that if you click on it, it will move automatically. And so this sort of gave new insight to, you know, these places that I've heard of, but I didn't really realize how big or how small or how many people are in each city, actually. You see Chicago? See how many people are in Chicago? It's a hugely dense area over there. And then Dallas, Texas down there, that's huge as well. Oklahoma City. So this is using a couple different map layers using D3. The tile layers are the NASA Earth at Night images and the labels. And then there's vector layers as well, which are the state borders. See these blue lines on top? That's using SVG to make an overlay of the state borders, so you see where the state borders are. And then I didn't really realize it before I made this, but most of the population in the US is concentrated on the east side. And on the western half of the US, the density is a lot less. It's a lot less. Most of the people are in California. So here's another example that uses D3 and SVG and a tree layout to show you the hierarchy of the world countries. So this is what it looks like in detail. You see that at the top level there's the world, and then there are the major regions of the world: Africa, Europe, Asia, Latin America, and then it goes all the way down to the level of countries. So for example, within Southern Asia, and you can zoom in here as well, you see, oh, here's Pakistan, Nepal, India is there in Southern Asia. And so wherever you are in the world, if you open up this graphic, you can zoom into your country and see, you know, where am I in the hierarchy of the world? You know, where is Samoa? Oh, it's in Polynesia. Where's Polynesia? It's in Oceania. And where's that? Oh, it's in the world. So I'll show you the code for this a little bit to get a sense that of how it's done. It's again SVG using D3 to make an SVG DOM element. D3.cluster is the part of D3 that does the tree layout here. And then, oh, there's actually there's an invisible rectangle on the top of everything to capture the mouse events for zooming, and that's a common pattern with D3. So it's a JSON structured hierarchy. And by the way, you can make requests to APIs as well. The D3 code would look exactly the same if you invoked an API here instead. That would make a database query on demand. And so you use D3 to make the links and also the nodes. And the nodes have text inside of them. And notice how the font size is a function of the depth in the tree. So if you see up here, the label for the world is much bigger than all the others. And as you get down to the level of countries, it gets smaller and smaller. So it's just to give a sense of what you can do with D3 in terms of tree layouts. So where's this data from? United Nations. And the United Nations had another data set that I got interested in when I saw this, and it was the migration of people in the world between all the countries. So the migration data had data for each pair of countries, how many people went from country A to country B in 2015. And so I wanted to visualize that. But if you visualize all connections between all the countries, it's like there's too many connections, right? So what I did is I aggregated the data to this other level where it's like the Caribbean, Micronesia, Polynesia, South America. It's the next level up from countries. And I made a visualization of migration. And this is what it looks like. Global migration in 2015. Let me see if I can fit it on the screen. This is using a technique called chord diagram. And you can use a chord diagram to visualize flows. So each chord here, meaning each of these shapes inside the circle, it represents flows in both directions between the countries. And so, for example, the bottommost shape here, it's the segment on the North American side is big, right? That represents the people that are going from the other part into Northern America, and the other part is Central America. So the number of people going from Central America to Northern America is huge. That's why the segment is large there. But that shape also represents the flow in the other direction. And the flow in the other direction is represented by the width on the other side. So you can see that the number of people going from Northern America to Central America is a lot less. So you can see the people are generally flowing into Northern America from all the other places. And that's what sort of stood out to me when I made this visualization. See the Northern America part? If you highlight here, you can see that for the majority, for I think all of these chords, the segment of people going into Northern America is far greater than the segment going out. So there's a mass migration into Northern America from all over the world. And I was sort of surprised when I saw that. And you can see other patterns, like, for example, in southern Asia, there's a lot of migration in southern Asia, but most of the people are staying in southern Asia. They're migrating from country to country within southern Asia. That's what that big blob here means. So I'll go into the code a little bit here. It's D3 layouts, D3 ribbon and D3 chord and D3 arc. These are the things that you can use from D3 to make a chord diagram. And it's great for visualizing flows. Here's another map visualization that I made. Migrant deaths over time. So there was a great project called the Migrant Files, where a bunch of journalists came together, and I think it was funded from grants. They collected this data about migrant deaths, people trying to reach Europe from other places in the world, like Libya and Syria. And each circle here is an event in which people died trying to reach Europe from these other places. And these journalists, they collected each of these events from news articles. So whenever there was a news article about an event in which people died trying to reach Europe, one of these journalists entered it into this database, and they did this since 2000. Somehow they got all the data of all these events from year 2000 to year 2016. And so I thought, oh, that'd be really cool to visualize, right? So I made this visualization, and this is a date histogram on the bottom. So it's a variation of a bar chart where each bar represents, I think, a month here. But you can use bar charts to represent units of time as well. And then there's brushing on the bar chart, on the date histogram. So when you brush, see that the map updates to just show the data from that region of time. So if you want to just see in 2008, what did it look like? You know, what are all the events in 2008? You can see these are where they are on the map. So I'll view this in full screen. And you can see that if you select maybe a year and you move it, you can sort of see patterns start to emerge. And one of the patterns I found interesting is that in 2014, there was a huge surge of events in this area around Tripoli. And then as you move forward in time to 2015, 2016, there's a shift to the border of Turkey. And in 2016, it looks like more deaths were occurring on the Turkey border over here. So I don't know that much about this topic, but the point is, if you visualize the data and give people these interactive views, you can discover things just by looking at the data. And so I would be curious to talk to people who know more about the topic. You know, why is it? Why is it like that? You know, I don't know, but I can see it from the visualization. And another way to see that is you can zoom in on the map. If you zoom into this area in Tripoli, see how the date histogram changes? You can see that most of the deaths around this area are in late 2014 and 2015. See that? But then if you navigate over to this other area, the Turkish border over here, you can see that all of these events happened in late 2015, 2016. So this is using a leaflet, by the way. It's not just D3. The map is done using leaflet.js, which is an awesome open source mapping library that's kind of like Google Maps. It's kind of overtaken Google Maps. It's great. And lastly, I'd like to just mention this other project I'm working on for Stanford University, visualizing very old vocal music. So this is a song that people sing. It's from like the 14th century. So there's people doing research about this music, right? And you can visualize the music, and this is what it looks like. And we've added these widgets here where you can see like what are the highest and lowest notes highlighted in red. And there's the same pattern here of brushing. This is called brushing. It's an awesome pattern that you can do with D3. And you can sort of zoom into certain parts of the song. You can combine the voices together. Each of these lanes would be a different person singing. And these are the notes. Pitch goes up and down, and time goes from left to right. So the idea here is just to communicate that visualization is a tool for understanding data. And data is kind of this digital mirror of the world, right? So by understanding the data, you can understand the world, or certain parts of the world that you have data about. And it's so powerful, and I think it's just amazing. And so that's the end of my talk. Thanks for listening. Any questions? Yeah, I think we have a microphone going around.
So, great talk. So these visualization, I mean, in terms of responsiveness, so what I do is I always destroy the D3 graph and then re-render it. Is there something across the responsive, I mean, in tabs or mobile devices or stuff we can do with D3, or some performance based, if you can tell something? Because always making it destroy and re-rendering it, I find it little disturbing for me.
So if I understand you correctly, the question is, currently what you do in your D3 code is you destroy the whole DOM structure and then recreate it every time the visualization changes? Is that right?
Yeah, I mean, yeah, like something like that.
Yeah, and so you're wondering what can you do differently? So kind of like React has the virtual DOM and the DOM diffing to increase performance, to improve performance. D3 has a great pattern, and it's called enter, update, and exit. And this can be used to reuse the DOM elements. So when your data changes, and by the way, this is one of the frustrations I have with the introduction D3 examples, or the ones you find on blocks.org, for example. Blocks.org is where you see these D3 examples, and usually when people want to use D3, they go to blocks.org, they find some example, they copy it, and then just change the data to be their own data. But the thing about those examples is most of them, and I'm guilty of this too, it just uses the enter part of this D3 pattern of enter, update, and exit. But if you use the full pattern, which takes a little bit of work to understand how to use it. But if you use the full pattern, then you don't have to actually destroy all the DOM elements and recreate them every time the data changes. You can use this pattern to propagate new data into the existing DOM elements and just change their attributes. And the enter part takes care of adding new elements, new DOM elements, for the new data that didn't exist before. And then if you have new data that has fewer entries, then the exit part of this pattern takes care of removing the DOM elements. And then the update part takes care of reassigning the properties of the DOM elements, like x, y, width, height, and that sort of thing. So yeah, I would recommend reading about the enter, update, exit pattern of D3 for that. Yeah.
Yeah, one more.
Sure.
So how would we, like, the responsiveness, if the window size is small, suppose in mobile, if I go to portrait mode or landscape mode, so how would I do something like that? I mean,
sure, this is a very common issue as well, because a lot of the examples, the first line says width 500, right? But what if your width is varying? So I faced this issue as well, and this is my solution. I made this example where if you open it, it resizes to whatever size the browser is, and it updates actually. So if I resize the browser, it will update like this. And you can use this pattern to, in conjunction with the D3 enter, update, exit, to resize the charts. Like if you're on a mobile device and you change the orientation, This pattern would fix that, and I'll just tell you what it is a little bit. So I'm using CSS to compute the size of the containing DOM element, and you can use any CSS. I happen to be using position fixed left, top, right, bottom are 0 pixels. This will make the DOM element fill the page. And then I have this redraw function that I'm calling once initially, and then you can hook into the browser event called resize, and then invoke this redraw function every time the browser resizes. And in this redraw function, these two lines here extract the width and height that was computed by CSS into JavaScript. So you can use them to set the scale domains, the scale ranges in D3. So this is one pattern you can use to achieve responsiveness, like resizing responsiveness. Yeah.
Hi, Karan. Thanks for the talk. So,
where are you?
here.
There.
All right. I wanted to know about the reusability part in D3. See, we were looking at reusable libraries that come with built on D3, like NVD3 being one of them, C3 being one of them. Can you comment on what are the libraries and what are the things that we should be looking at? One of the major things that when we are looking at these libraries is the data that it gets to handle. Right? If over the top of your head, if you can suggest few of these libraries that we should be looking, so that would be great for us.
Sure, yeah. So the question is, what about reusable charting libraries built on D3? Yeah, I mean, so my thought about this is, there's this canonical work by Mike Bostock called Towards Reusable Charts. And most of these reusable charting libraries are based on this post by Mike Bostock. And he explains how, his take on how you could create reusable chart elements and how to create these accessor functions that are setters and getters, depending on if you pass them an argument. And so NVD3 was kind of one of the first of these reusable charting libraries, and it's really great, and a lot of people are using it. There was some controversy about the licensing at some point in the past, but I think that got resolved. This is a great one. This is a great one. It's, but with any of these charting libraries, once you adopt it, you take on the burden of the abstraction that they created. And so typically it limits how much you can customize the visualizations. But yeah, NVD3 is a good one. There's C3.js. Whoops. C3.js. This is another very good one that a lot of people are using. I think I saw this in some Indian government website being used. Yeah, and a lot of these handle the updating data, but like you said, each one of them imposes restrictions on what format the data needs to be in, what data structure it accepts, right? So that's part of the burden of their abstraction. And then Vega, firstly, there's Dimple. Dimple.js, this is another one of these reusable charting libraries. This is also very good, very good. This one has small multiples, which is pretty impressive. But sort of probably the king of all of these is Vega. I wonder if it'll come up. Oh, Vega helmets, right. Yeah, this is sweet. This is from Jeff Hare and his group at University of Washington. Just to give you a sense of the heritage of D3, D3 was created by Mike Bostock. When he was at Stanford University, his advisor was Jeff Hare. So he created D3 in Jeff Hare's research group. Jeff Hare's research group is continuing to do awesome work, and this Vega project is one of their sort of main initiatives, and they've got a bunch of other stuff that's built around Vega. But this is a really good one. This is a really good, let's see if I can open up the demos. Vega editor. Yeah, so the idea with Vega is it's not the same as the other ones in the sense that the other ones give you like different classes that you can instantiate for different chart types, like bar chart, scatter plot, named charts. But Vega is different because it's based on the grammar of graphics. And you give it this JSON data structure that specifies the scales and the axes and what the marks are. So it's a totally different approach than the other libraries. So I would recommend looking at Vega. But again, you take on the burden of their abstraction, and it becomes difficult if you want to customize it to an extent beyond what they have foreseen in their code. But yeah, and also there's React, this sort of React craze, where everybody's using React. And D3, any of these libraries could probably be, here it is, React D3 boilerplate. You can encapsulate any of these things as React components, and I see a lot of people wanting to do this, and I think it's a great idea. So you just use the React component as sort of the abstraction barrier, and then just figure out what properties you want to pass into the visualization, and then use the D3 library to update the chart. Yeah, does that answer your question?
Hello?
Yeah.
This side. So if 2 or 3 datas overlap at a one data point, so how do you handle it?
Yeah, so the question is, if 2 or 3 data points overlap at the same point, how do you handle it?
Yeah, especially in case of bubble chart.
Right.
So the color become more dark, but it's very you don't differentiate between if you need to attach some event and show some pop-up, so you didn't get the exact data.
Right, so this is a question that's really about data visualization. It's not specific to D3. Yeah, like if you have a bubble chart, meaning a scatter plot with different sizes, and actually I ran into this with the migrant deaths map, and I was very frustrated by it. See, if you zoom in here, you can see that there's this one place in the ocean, right here, where all of them are overlapping. So I think this is the question you're asking, right? Exactly this case, where they have the same latitude, longitude. So no matter how much you zoom in, they're never going to spread apart. They're the exact same point. And so it's like a fundamental problem of this way of visualizing, where each record in the table maps to one circle. There's other ways, like hex bins. Anyway, binning. You could have other approaches where if you want to perceive the density rather than each individual point, you can impose a grid over the data and then compute how many points fall into each bin. Let me show you hex bin D3. Like, hex bins are great for this. I'll just go to the images to give you an idea. So like, here's one example where instead of plotting one visual mark for each row in the table, they do some aggregation and they compute how many points fall into each bin. And then based on that, you can size the mark or color it differently. So that's one approach. And another approach to dealing with this is to have jitter in the plot or use a force-directed layout. Like, here's an example where the ones that fall on the same point, they actually collide and they push apart a little bit. And actually, you can turn it on and off. So here's with the collision detection on. See, the points get spread apart. It's a trade-off because it's not really honest anymore. It's not actually plotting the data, but it shows you that there's multiple points in each spot. So yeah, there's a couple of different ways you can handle that situation, but it's definitely a problem. Yeah.
Hi. Thanks for the talk. Am I audible?
Sorry?
Am I audible?
Sort of.
Clearly?
Not really.
Okay, yeah. So the question really was, how did you go about choosing what visualization to use? So even in D3, we have lots of options. So
right, how do you go about which visualization to choose? So this comes to a backup slide that I had. So there's actually a huge body of work about data visualization theory and how do you choose which visualization to use for a certain data, right? So when you have a data table, you look at the columns of the data. The columns fall into a few different types, right? You could have strings, that's called ordinal or nominal columns, where the strings are just different entities, right? And then you have quantitative columns, where it's like a continuously varying number. And then you have latitude, longitude, which is kind of a special case. Then you have dates as well, and date histograms. And so depending on how many columns you have and what types of columns they are, you could think about how do you map each column to a visual variable or visual channel. So this graphic right here is from Jacques Bertrand. He's this French guy. In 1967, a long time ago, in this great book called The Semiology of Graphics. And this is where he kind of lays the foundation of data visualization as a field. And keep in mind, data visualization is a lot bigger than just D3. You know, D3 is the modern incarnation of all these ideas, but they've been around a long time. So these are the visual channels that you can use. There's marks and channels. Marks are the shapes, like rectangles, circles, and then channels are things that you could apply to these marks to modify them. For example, size on the top. The size of a mark can vary, and size is best used to encode a quantitative variable, or an ordinal variable, meaning it's different categories like small, medium, and large, but there's no distinct quantity, no exact quantity. Size is great for that. And then there's value, which is distinct from hue. There's the two components of color. So the value part, you know, how bright a shape is, that's great at encoding quantitative data as well, and also ordinal data. But it's not really good at encoding nominal data, where you have like different people's names, for example, you know. But hue, on the other hand, which is another component of color, hue is great at encoding different nominal values, like people's names, or state names, or, you know, identifiers. You can distinguish between different things with color really well. And then there's orientation. That's not really used that much, and texture, that's also not really used that much. But then in the middle, there's X and Y. X and Y are the most powerful channels that you can use. So if you have a data set, a data table with like 10 columns, and you know which columns are most important to you or your audience, you should use X and Y to encode those columns. And X and Y they're very powerful because you perceive them right away. You know, before you even get to think about the chart, you see how it's laid out generally. So they're very powerful in terms of perception, and X and Y can also encode quantities and also different entities. Like we see in a bar chart, you know, one of the axes encodes different things, and the other axis encodes a quantity. So hope that answers your question. I believe we're out of time.
Hey, Karan. So my question.
Where are you?
I'm here.
Okay.
Upstairs. Yep. Yeah. So you mentioned that if we are drawing circles, we should use a square root scale. So if you could just give some more explanation of the rationale behind that, and if you could give other such examples of which scales to use for which kind of shapes.
Sure. Yeah. The logic of using a square root scale to encode the radius. So keep in mind, you're mapping data to the size of a circle, right? And how do you compute the size of a circle? Well, in SVG, you specify it as a radius, which is different from the area. But when you see a circle, when you look at a circle, you perceive its area, right? Because you're used to seeing things in the physical world, right? And so based on the area of something, that's how you perceive how big it is, right? So the idea is that, you know, when you use the size of a circle, it's best for encoding like countable things or quantitative things that start at 0. You could have a quantity of 0 of something. In that case, it would be a circle that's so small it doesn't exist, right? And that would be the end of your scale. And then the other end of the scale would be the biggest circle that you could have, which could be a custom value, you know. But the way that it should vary between no circle and a biggest circle is a square root scale. Because if you use a square root scale where the range starts at 0, then, only then, the size of the circle, the area of the circle actually encodes the data. So that's why you should use a square root scale when you compute the radius of circles for quantitative values. There was another question that you had, but I don't remember what it was. Or another train of thought. It looks like we have to stop. Sorry, I forgot what the other one. Thank you very much. Thanks, everyone. We need this one. Is it off?
Please note that the food tokens handed out to you have to be used for exchange for food downstairs. If you run out of tokens, want to buy tea, etc., loose tokens are available at the counter. Please go and purchase them. Kindly do not exchange in cash at the food counter. If you have tokens left over at the end of the day, you can use them to exchange for merchandise at the counter.
Hello. Hello. Thank you. Okay. Oh. The USB. Okay. It's what? Yep. Yeah. Hello, good morning. I'm Rahul Yadav from housing.com. So, hi. Today I'll be talking about building fast and performant apps. So, this talk is mostly our learnings and experiences we had building Housing Go, our new revamped mobile website. Let's start. So what comes to your mind when you think about fast and performant apps? There are a lot of things: first paint, page load time, document complete, DNS lookup, and a lot of other things, right? For the scope of this talk, we'll be focusing only on 3 main metrics that we'll be tracking throughout this talk. That is the first paint, the first meaningful paint. The first meaningful paint refers to the time when user actually sees the actual content he has done the action for. And the first interaction I mean first JavaScript enabled interaction. That is when your JavaScript is downloaded and ready to downloaded and executed, and you can handle users interaction via JS. So one important factor to all this is your critical rendering path. It's the part that the browser takes to render the first view to the web page. It has few components in it. You're downloading the first HTML, downloading your CSS, downloading your JavaScript, processing them all, and then displaying the content. This talk goes something like, we'll take a very unoptimized version of Housing's mobile website. We'll look at the numbers in the starting, and then we'll go about improving the 3 metrics that we defined. So the first version of the website looks something like this. So all the videos are done on 3G connection and from Dulles in Chrome, emulated as a browser. Let's see again. Right? So many of you have noted that the first paint happened at around 5.2 seconds. There was some meaningful content on the page at 7.4 seconds, and the first JavaScript enabled interaction happened at around 6.9 seconds. I'll come to how we determined this time in the later half of the presentation. So let's talk about how to optimize the first paint. So the first pixel that's painted on the web page depends basically on how soon or how well you download and make your CSS home. Download your CSS and make your CSS home, and then your render tree and the layout happens. Right? For this version of the website, the code looked something like this. You have a head tag. There was a link style sheet tag pointing to our CSS, and then body and rest of the page. Let's look at how does this waterfall looks like. You see the first request went for the HTML, then your CSS, the second request is for CSS, and when the CSS is completed at around 4.7 seconds or 4.8 seconds, then your start render happens, right? So that's kind of render blocking. By render blocking, I mean the browser had to wait for this request to be completed to display the first pixel on the screen. How can we avoid this? The answer is the inlining critical CSS. The word critical is very important here. Critical means only the CSS required to display the above the fold content that the user is seeing, right? Inline CSS code looks something like this. So we have divided a CSS into two things. One is our app CSS that's global throughout the website, and one is search, the search view CSS that's for the page that we are looking at. So this is the heaviest page of our website that has a lot of API calls and a lot of things happen on the server end and on the client end also. So when we inline the CSS, let's look at how does the waterfall looks like. So you have eliminated, if you see the second request, you have eliminated the CSS request. Although you increased your DOM, your first index HTML size, but that helped you bring down your first paint from 4.7 seconds to at around 3.5 to 3.6 seconds, right? Let's see how does it look like if you compare the two side by side. Right? So the first paint has also moved down to 3.8 seconds, and the first meaningful paint has also moved down to 7 seconds as compared to what we had earlier. So these were the numbers earlier, and this is what we did with it. Also, the first JavaScript enabled interaction time moved ahead because now your JavaScript is started downloaded much earlier than it was being done before. Cool. So that's how that's how we improved the first paint of the website. Now moving down to we'll skip first meaningful paint for the end, and we'll continue to first interaction. Moving to first interaction, I'll explain how we have architected our website. So each page has index.html. It has 3 JavaScript files that are needed to actually execute or enable the user to interact using JavaScript. We have vendor.js, app.js, and vue.js. Vendor.js is mostly bundle of JavaScript files that rarely update, and it's mostly a collection of libraries that are globally there, like React and then everything else. We have app.js. App.js is mostly the bundle of JavaScript files that have all logic of routing or some global functions that are required throughout the application. We have Vue.js. Vue.js is basically our file that controls the JavaScript interactions for the given view or the given page that is being rendered on the website, right? To improve the first JavaScript enable time, it's very important to download your JavaScripts as soon as you can, and also execute them as soon as you can, right? Our application being a single page application, we wanted all these JavaScripts to download in order and execute in order, right? So that's very important. The execution in order is very important. First vendor.js is executed, and then app.js, and then Vue.js. Let's look at the different techniques that are available to download JavaScript files currently. So we have plain script tags, right? Plain script tags are just normal script tags with src pointing to your CSS resource. And the good part is they'll download your JavaScript together, but it's executed in order one by one. Like first vendor.js will be executed, then app.js will be executed, and then your Vue.js will be executed. It's also parse blocking. So anytime your browser encounters a script tag in your HTML, the parsing of the DOM stops. The browser downloads the resource, executes it, and then move ahead, right? So they are not good if you have multiple JS files or you have dependency of multiple JS resources. There's one more defer attribute to script tags. What defer attribute does is it makes your script tags non-pass blocking. The browser don't wait for the resource to be downloaded and executed to continue parsing of the DOM. But one thing you get is that you have made your JavaScript resources asynchronous. They'll be downloaded parallelly, but they'll be executed only just before the document loaded event is fired. So if your page has a lot of images or a lot of other resources that are somehow downloaded before this event, and it takes and they pushes this event to a longer time on the timeline, then you are in a way delaying intentionally the JavaScript enable time for a user, right? Then we have async attribute on script tags. Async attribute is wonderful. It makes the script tags non-pass blocking. Also, it will execute the JavaScript resource as soon as it's available in the browser, right? But the problem we had with this is because script tag, async tag will tell the browser to execute the resource as soon as it's available. We were not able to maintain the execution order of the JavaScript resources that we needed. It was very important for us that this execution order remained constant throughout the website. So this kind of didn't work for us. We did a bit of research, and after doing research, we landed here. So what's this? This is a function that's appending script tags with given source in your document. So the good part about this was that dynamically injected script tags are by default asynchronous. They don't stop the parsing or rendering of the document in any way, right? Also, by telling the browser to set the async attribute false, we were telling the browser that don't execute them asynchronously, execute them in the order. So for us, this was the kind of thing that we were looking for. So this gave us both downloading our resources in a non-parse blocking way and maintaining the execution order. So we were not very much convinced by whether it will work for us or not. So we tried to measure few things. The things we measured were when does our app.js load, when does our Vue.js load, and when did the component did mount of your Vue gets called. That's for the JS enabled interaction, right? So we used this API that's available, window.performance.mark, and we kept each marks for different at the bottom of different JavaScript files, and one at the end of the component did mount. We ran we did it few times, and this is and we plotted the data on the graph. So this is what it looked like. So on the x-axis you have the runs, and on y-axis you have time. So if you see for app.js time, for the app.js execution time, the defer technique was taking the highest time, right? Then came the inline scripts. So defer was taking highest time because it's deferred till the document loaded event is fired. And inline script because it has a few files before that, the vendor.js file. But to our surprise, execution time for our app.js was very like low, a difference of 1.3 seconds to 1.4 seconds as compared to the other two techniques. This gave us a bit of confidence that, okay, this might work. We saw the same behavior for our Vue.js, and the same behavior for our time to interaction, right? So that's huge gain of around 1.5 seconds, more than 1.5 seconds, what we got to enable user to actually start interacting with the page. Yep, so that's what we went ahead with. We did some polyfill for IE and other browsers. But this, our general audience of like the 90 percentile audience is on Chrome, so this worked really well in Chrome. And like from the metrics being the first interaction time at being 6.5 seconds, we brought it down to 4.7 seconds, right? That's huge gain in enabling the user to interact with your page, right? We did this, but this had few cons to it. Generally, dynamically injected script tags are considered harmful, harmful because browser has thing called preloaders or pre-scanners. So whenever your document is being passed, browser or when the browser's main thread is stopped at rendering something or doing some other function, the browser preloaders or scanners peep ahead in the document and they look for script tags or native script tags with link tags or native image tags with sources. And whenever they get those kind of tags, they download it ahead of when actually it's called by browser, right? So this gives browser the capability of downloading resources efficiently. So this part we missed. We couldn't get the advantage of browser preloaders. But then browser offers you some other meta tags that helps you tell browser that, yes, we have this resource and download this for us, right? So those are called pre-browsing meta tags. There are 4 to 5 pre-browsing meta tags. Let's start with DNS prefetch. So what DNS prefetch does is we use CDN for our assets, and we have multiple CDNs, one CDN for assets, other for images, and so on. So we definitely know that we are going to make connection to this CDN for downloading our asset. So this, by putting this tag in our head, we tell the browser that make an initial connection to this, so that whenever the request goes for that resource, we save this time. Like we don't waste time in resolution, doing DNS resolution for that domain. Great. Then we have pre-connect tag. What rel pre-connect does is, with DNS resolution, it will also do TCP handshake and TLS negotiation. So that actually helps you to eliminate a lot of time when you have resources coming in from multiple domains. So that's what we are currently using in our code also. Then we have a very powerful meta tag, link pre-render. What this does is, it will, if you give something like link rel pre-render and an href pointing to a page, what the browser will do is it will actually load the complete page in the background. And say you have a website which only have you have a page which only has A and B option, and somehow seeing the data, you know that user is like 90% of users click A. So if you give this tag in your head, and tell the browser that render my page A in background, what the experience that the user gets when he or she clicks on page A is that it's almost instantaneous for them, right? Browser has already made the rendered the page, and it's available right there for the user. But use this tag very cautiously. If you put a lot of pre-render tags in your head, it will stop the browser. It may choke the browser, like the network may be very populated and may not be free for the contents of the actual page. Like moving ahead, we have a prefetch tag. Prefetch tag is basically for few resources that you definitely know are going to be required on the page in future. The good part is that it's optional, like the implementation is optional for few browsers, and the download priority is very low, right? So say you have some asset in your page that's a very, an image that's required below the fold, but it's kind of big image, so you want to tell the browser that start loading this image whenever you get time. So you can do this using these tags. This one more powerful tag, oopsies. Yeah, so this one more powerful tag, that's preload. Preload has one benefit over prefetch, is that the resources that you define using preload are on the highest priority of fetch, and they are necessary for the current navigation. So browser tries to download them as soon as it's possible for it. So using these tags, we were able to eliminate the issue of not telling browser preloaders or pre-scanners what resources we'll be using on the page. And also it gave us an improvement of 0.1 seconds in the first interaction, enabled in JS and enabled interaction time. So far we are at this pace. First paint is at a 3.7 seconds. First meaningful paint is still at 7 seconds. First interaction has come down to 4.6 seconds. Right. Let's talk about first meaningful paint. So the first to talk about this, let me introduce the two kind of applications that we have. So client-side rendered applications and server-side rendered applications. So what client-side rendered applications are, generally your client will send a request to the web server sends a shell or basic HTML with few links of CSS and JS back to the client. Client processes it, make the API call required to show the data on the page, and then the data is available to the user, right? So the first meaningful paint that happens in these kind of applications is little bit longer as considered to what happens in server-side rendered applications. So server-side rendered applications look something like this. The client sends request to your web server. Your web server internally makes API calls, which are faster because there's no network latency and no network issues. The browser processes the data, makes the DOM string, sends the full page back, right? And the user sees the page. Yes, by doing this, you increase your first HTML that the browser is downloading. But when we were developing our mobile website, our main aim was to show the actual content to the user as soon as we can. So we went ahead with our server-side rendered app that for our mobile website, and the difference looked something like this. Right? That's a huge win over the content that's shown to the user. So these metrics move down to these numbers. Your first paint increased a bit because your initial document size also increased. And your first meaningful paint came down from 7 seconds to 3.8 seconds. That's almost 4 seconds, 3 seconds. And that was huge for us, showing user the content what he has intended for as early as we could. So apart from this, we did one more thing. So continuing on the philosophy that just push the response as soon as possible. When we were analyzing our pages, there were few part of the pages that were almost constant for every route. So the head part with the CSS and few links was almost constant for every route. So what we did is streaming HTML or streaming the response from the server. So our first meaningful paint for client-side rendered looked something like this. So the request came in, the browser sent some chunk earlier, and then it made the API calls and then sent back the remaining chunk. I'll show you how it looks in a minute. So this was the code that we used as soon as a request came in. Ours is a Node and Express app. So this is the first middleware the response comes in, and we just send this header back to the browser. This is just a 4 KB chunk that is sent back, and it looks like something like this. It has few pre-connect tags to the domain we are going to make connection to, and at that time we were using prefetch because preload just came in latest Chrome. So the prefetch, tags enabled us to tell browser to actually start downloading these resources. So you can see the request for these resources going on. And then once the server was done with API calls and processing the complete data, we sent back the response completely. And so the initial index HTML, the size increased from 4 KB to 13 KB, right? That's how streaming works. I'll show you the timeline, how it looks like. So you see the first request that's going, the first chunk that came in, it was processed. And as these first 4 are preload tags, the request is sent via preload tags, and then the remaining HTML comes in, and the request for the actual request that's from the bottom of our body is then sent again. So that's how we tried to push the JS files for the user as soon as possible. Yep, that helped us a lot in improving our first interaction time. So our first interaction time went down more by 0.4 seconds. Yep. So that's how we optimized each and every part of what we were tracking. Yep. Thank you. I can show you the current one we have, I guess. It's not working. Okay, it's not working. It's around 3.6 seconds now, and the JS interaction has also moved down to around 4 seconds. So if you just run a web page test, you can see that. So.
Hello?
Yeah.
Yeah, hi. Here. Yeah, Rahul.
Oh, hi.
Yeah. So with the multiple meta tasks, as we discussed for improving the performance, have you also considered the domain sharding as one of the key factor in improving the performance?
Yes, definitely. So we have enabled H2 on all our CDNs, so that helps us push the resources with a single connection. And definitely, so we have, so for our main assets, we use assets0.housingcdn.com. For our assets that are not very important to us, we use assets1, and for our images and all other things, we have IS1, IS2, IS3. So yeah, that definitely helps.
Okay, so all of those were a canonical name or actual different servers?
They are subdomains of the CDN that we are using.
Okay, all right, thanks.
Hi.
Yeah, hi.
Hi. So your full stack is completely in JavaScript, is it? You are using Express in the
Can you
backend
speak
for.
louder?
You are using Express in the backend for REST APIs as well.
Uh, yeah, for making the API calls, yes.
Okay.
We use promises
No, no.
to.
I'm sorry if I was not clear. The APIs are written in Express.
No, no, no.
No.
We have different services in backend. Few on Ruby on Rails, few on Go. So
Okay. And what's the database you are using? If
it's Postgres mainly.
Postgres, and you're using the
We use
JSON.
Elasticsearch for uh, maintaining our fast responses of
No,
our
I'm
list query.
asking because when you talk about first print and people are talking about first print from past one day, the backend also plays a role, right? Because that is
Yep.
giving you the data back.
Yep.
So that's why I'm trying to understand. So you have Ruby APIs
Yep.
interacting to Postgre.
Yeah, we have a layer of memcache and Elasticsearch, so that part is pretty well taken care of, and the APIs from the web server are within the same VPC, so there's no network latency. They're really very fast. So
Okay, thank you.
yeah,
Hello.
yeah. Hi.
Hi. How did you manage to extract your critical CSS?
What?
How did you manage to extract your critical CSS from the bulk of CSS?
Okay. So if you open Chrome DevTools and you see the stack of the network request of Housing Mobile, we have something called lazy CSS, lazy view CSS that kicks in after the window load is happened. So the way we have separated the chunks is that app CSS only has rules for few classes that we use globally, or say for our header that's constant in all the pages, or for just to show the first menu of our side menu. We have even kept the side menu CSS in the lazy view CSS. So by doing that, we are like, the hypothesis is that user actually takes few minutes to actually go through the content that's provided on the screen, and by that time we would have downloaded lazy view CSS. If not, the screen may look, the action may feel unresponsive for the first time.
There are few online tool as well, like CSS extractor, and
Okay.
there is one Chrome extension as well.
Right.
How reliable it is?
We have not tried tools like that,
Okay.
but in our experiences from doing multiple revamps and building the mobile website again, it's it's recommended that you write your CSS keeping in mind all these things from the very start, and
Okay.
you try to minimize as much as you can.
Okay, thank you.
Hi.
Hi, where? Hi.
So I wanted to ask you a bit more about HTML streaming that you mentioned.
Yep.
Can you please elaborate more on that?
Okay. So as Abhinav also mentioned yesterday, we are using almost the same stack. We have Nginx as a reverse proxy. So there's a flag in Nginx proxy buffer that you set to false. And when your response is coming in your Express app, you keep on writing small chunks of response and in small chunks in the response, and the stream automatically takes it back to the browser. So that's how we are doing it. Yep.
Hi, Rahul.
Hi.
So, interesting tags which you specified, but I think they are Chrome specific, right?
Right.
What do you do about other browsers that you need to support, like Mozilla and stuff?
Okay.
Is the experience any different over there, or is it the same?
I guess we just had to do something differently for UC browser because that doesn't support dynamically injected script tags. So there, the script tags are basically plain script tags that are at the bottom of your page. But for all other browsers, we used a polyfill. If I'll share my slides, there's a link to it which tells about the polyfill that we are using. That's mostly for IE, and all other browsers by default support this behavior. So we like there wasn't actually much effort in making it work across all browsers.
Hello?
Yeah. Hi.
So another streaming question. So how do you handle the HTTP status for streaming responses? So when you are sending the static chunk first, it's always going to be a 200 OK, right? But your API call may fail. So
the connection is always open. Until unless you end the response, the connection is live.
But you can send the HTTP status only once, right?
Yeah, that's sent when it's when you do response.end. So, like, Express handles it internally. Like, I'm not sure I can completely answer that. It may take some research, but Express does it automatically. So.
Thanks for the talk. Can you elaborate a little bit more, since you already separate out? Since you already separated out vendor,
right?
And what was the need to differentiate your GS? So
Okay. So generally, if you have, we have used React Router with dynamic chunks. So if you don't separate out your views in different chunks, everything just comes at the top of your router declaration. So your app.js actually becomes very big, and if all the JS that's not even required to enable the interaction for the given page also gets downloaded. So that's not a good practice to do. That's why. Yeah. Cool. Thank you.
Okay, then thanks everybody. We'll resume back at 11:30. No, sorry. We'll resume back at 12.
Harshal.
Harshal.
announcements.
Hi everyone, welcome back. A couple of announcements before we start. We have loose food coupons that are being sold downstairs. We have a dinner at Wood Rose today. If you guys are interested, you can buy registration passes for that outside. The dinner's at 6:45. T-shirt counter is open. We have 2 BOF sessions again today. They will not be telecast live. And please fill the feedback forms. Oh, and Collective held a contest yesterday. The winners will be announced at 1:25.
Hello. Can you guys hear me?
Our speaker is Aziz Khambati from housing.com.
So, hi, I'm Aziz Khambati. The slides are available. They are a pin tweet, and they're also available over here. Okay. So we are spoiling ourselves with faster websites. What's our generation's perception? If you respond in less than 100 milliseconds, it's considered almost instantaneous. Within 1 second is not bad. If you take roughly 10 seconds, the user's mind starts to wander. And if you're taking more than 10 seconds, we are never ever coming back. So at the end of the day, it all depends on what the user feels, what the user perceives. And that is what I'll be talking about, perceived performance. These are the key points. I'll be talking about the Rail performance model. Then I'll be talking about passive event listeners, the new CSS contain property. And then lastly, I'll be talking about speed index. So this is the Rail performance model. It was put forward by the Google developers. It stands for Response, Animation, Idle, and Load, RAIL. So it sets guidelines which are in areas which are important for perceived performance. So here we have the guidelines. I'll be explaining in detail each of these guidelines. No need to get worried about so much text on the screen. So let's start up with response. So response to clicks in less than 100 milliseconds. This can be anything, response to clicks, toggling form controls, etc. And you can show anything. This can be a simple state change or a color change. If you're taking more than 500 milliseconds, show something. This can be anything like material design's ripple effect. Or you can show intermediate state transitions. Like over here in this example, we have Housing Go's search page. And when the user taps on a property, what happens is that we have some of the details already with us, like the name of the property, the price, etc. So what we do, we show that information upfront and make a network request parallelly, so that when that comes up, we'll show that. So the user does not get a sense of waiting, and he can start viewing the data when it comes up. And last option, if you can't show any of that, show a loading spinner. But make sure that it's your last option. Next up, another section in the response category is response to swipes. So now you want 60 FPS. to get 60 FPS, 1000 divided by 60, you have to respond in less than 16 milliseconds. So how do you get that? Avoid heavy scroll, listeners. Or if you can, just don't add them at all. Or you can rate limit your listeners using debounce or throttle. The debounce is just something like you wait for X milliseconds for your event to stop firing, and then you run your function. So in the example, B and C events happened very close to each other, but we waited for some milliseconds to actually run our C function. Similarly, throttle is proper rate limiting. Your function is run only once every X milliseconds. Like in this example, X and Y happened immediately after A, but we had already run our function once in that time frame, so we did not run it again. So if you can't do any of these, your last option is passive event listeners. It's a new property which was recently launched. It's available in Chrome and I guess Opera. It's coming soon to Firefox. It's coming this month in Firefox 49. So what are passive event listeners? So when you scroll in onto a div with your mouse, what happens is that if you want to cancel that scroll, what you'll do is that you'll prevent default that event. Now, a classic example is when you scroll on Google Maps, what it does, it will prevent default, and so that it can zoom into the map. Now, the browser does not know if your listener is going to prevent default or not. So it has to run your function so that in order to determine whether, is this function going to call prevent default or not. So that which causes sluggishness if your function is very slow. So what is the option? I solemnly swear that I won't prevent default in my scroll listeners. So through passive event listeners, you tell the browser that my function will not be doing prevent default or does not need to prevent default, and it can go ahead painting the next frame. So here's the syntax. The third parameter is where you used to send your captured true false flag. That is now changed to an options object, and you can send a passive true parameter key so that to tell the browser that this is a passive listener. Also, if you still want capture true false, you can just add a key capture true false. How to determine if browsers have this feature available? You just add a test listener. You pass in an option object with a getter on the passive key. If it checks for the passive key, you are sure that this browser supports passive event listeners. So here's an example. So over here, I have my timeline enabled from DevTools. And what I'll be doing is, I'll be scrolling. You can see that, the frame rate drops when I'm scrolling. Let me give you an example with prevent default. You see, I cannot scroll. Now, I add passive event listeners. Frame rate constant, 60 FPS. Cool. So your browser renders the next paint before it calls your function. Again, if you call prevent default with passive event listeners, it will fire that, what does it fire? Unable to prevent default inside passive event listener invocation. Cool. So passive event listeners. Next up. Or if you want to disable, if you want to prevent default, you can add the touch action none property. And if you have a horizontal carousel where you want to pan on the X, you can pass pan X. Another area where scrolling performance gets degraded is infinite lists. So what you can do is make sure that your DOM elements remain constant and you get smooth scrolling. Over here, we are using React virtualized for enabling the infinite list. Okay, so some tips for React users. Sorry again for React. So now you guys know that React is a virtual DOM diffing library. What it does, it keeps the entire virtual DOM in memory. So what happens at the time of patching? At that time, what it does, it will have the old DOM, virtual DOM, and then it will generate the new virtual DOM through the new state, and then it will compare those two virtual DOMs. So at the time of diffing, you have twice that amount of virtual DOM in memory. So what happens just after that? After your patching process completed, a huge amount of memory resources get freed up, and that might trigger a garbage collection. So just when you wanted to animate, the garbage collector says, stop, I got a GC, and you drop some animation frames. So what you can do to avoid creating new objects in your render function, avoid creating new functions. Like over here, we are creating a new on-click listener, a new function every time. Similarly, bind, what it does, it creates a new function. You should not be doing this. What you can do is you can bind your listener to your instance in this constructor, and so that only one instance of that function remains. Another trick that you can use is you can hoist up your static content. Static content which is independent of your props or state, and so that only one instance of that particular virtual DOM is generated. But this does reduce readability. You have to scroll up and down. Oh, what is my hoisted title variable? Oh, it is my awesome title. So what do I do? No worries. There is a Babel plugin just for you. If you're using React, you must be using Babel to transpile. So you can add the transform React constant elements, and it will automatically hoist up your constant elements for you. Heck, you can even add the React preset, which automatically adds all of these optimization plugins for you. Next up, define pseudo component update. If you return that my component has not changed, it will skip the render process entirely. Next, in the Rail performance model, we have animate. So again, we saw to get 60 FPS, you have only 16 milliseconds per frame. So we saw earlier the render pipeline yesterday. Just a quick recap. If you have JavaScript, your JavaScript will apply your attributes. It will change your styles. Then your style is computed. It takes up your DOM, and it takes up your CSS and creates your CSS SOM. Then layout happens, which is sort of like wireframing. Your various elements are positioned on the screen. And then paint happens, which it paints each of those elements. And then composite happens, where it takes up those elements and then it stitches them together. So these are the properties which trigger different parts of the pipeline. The higher up you start, the longer it's going to take. So for example, if you're modifying something like margin and height, it's going to change the position of the elements. So it might change the position of elements that are below it also. So that might cause a relayout. If you're modifying properties like color, background color, etc., you'd only need to paint again. You know that the element is in the same position, so layout might not happen. Next up, if you animate properties like transform and opacity, what happens that it takes up the already painted layers and just stitches them together in the composite factor. So what you aim is that you start as low as possible, so that only that particular step happens. So what do? 4 things a browser can animate cheaply: transform, translate, scale, rotate, and opacity. You may need to add the translate Z0 or the translate 3D 000 to push the elements to a different layer. To pushing the elements into a different layer such that they are painted individually, so that they can be reused during the composite layers. Also, there is a new translate 3D 00 is a hacky way. What if you want to add a different value to it? So you can use the will change transform. That will also push elements to a different layer, but make sure that you don't push everything to a different layer. It's going to slow down your render pipeline. It'll create different small GPU renders of all those different elements. To determine which property triggers which process of your render animation pipeline, you can check out csstriggers.com. It gives you an entire list in which browser, like in Blink, Gecko, what, like the float property will trigger layout operations again, etc. All CSS properties you can check out over here. Next up, let's talk about the new CSS contain property. This was introduced in Chrome 52 and Opera 40, and it's coming soon to Firefox. It has huge developer support. So what is? If you define contain layout, you tell the browser that my elements which are inside, the elements which are inside my current, any descendants of this element, they do not affect layout. So for example, affect layout of any other elements. So over here, we have my child div, whose layout, whose position does not affect my untouched div. So what happens is that layout of the entire document does not need to happen. Only if something, a descendant of your particular element changes, only layout of that particular element is done again. So yeah, so pipeline, this is the highest performance benefit that you get from the CSS contain property. Next up, contain paint. So with this, you're telling the browser that no descendant will display outside my contains bounds. So it's sort of like overflow hidden. So if you have position absolute and position fixed elements, they are positioned relative to their first non-statically positioned ancestor. If there is a closer contain ancestor with contain paint, they will be positioned relative to that ancestor. So it becomes a containing block. It becomes a new static context as well. So z-index works only for elements which are not position static. So now if it is contain paint, z-index will also work. So we saw earlier that will change pushes elements to a different layer. Similarly, contain paint also pushes different things to a different layer. So simply put, contain paint is equivalent to overflow hidden, position non-static. Maybe it's, if you've given absolute or fixed, it will take up that. If not, it won't be static. Will change transform to push elements to a different layer. Contain size. So with contain size, you tell the browser that my element size are defined and its size won't change. So any descendant, like if my descendant grows big, it has a lot of text, my element size will not be affected by that. But if you don't define your element size, they will be rendered 0 cross 0. So make sure that you've defined your size if you're using contain size. It's not much of a performance, but okay. Contain style. So contain style is like, is you're telling that any styles of a descendant will not apply outside that particular descendant. So for CSS, that is cascading style sheet, where your styles flow up to down, this actually does not give much of a containment, but it can be helpful for CSS counters, where your counter is used in various elements. It is in no way related to the shadow DOM like scope styling. So we have more shorthand as well, like there's contain strict, which is all four. It is a shorthand of all four. It is useful if the dimensions are set, because contain size requires that your dimensions are set. Next up, contain content. What it does is that it's a shorthand for layout plus style plus paint. So it's all except size. So it doesn't need dimensions. So this is what you should be by default using, because it helps you. It's not that restrictive as contain strict, but you can easily use it in your application. So here's an example of the performance improvement. Previously, when we had no containment, the layout route was the entire document, and 5 nodes needed layout. Now the layout route is div box, and only 2 nodes need layout again. So you saw that the layout process, its time decreased as well. Next up, JavaScript animations. So avoid animating using JS. If you have simple animations, you can use CSS instead. So we saw earlier the render pipeline. Now JS animations will start right up top, and on every frame, your JS will get executed. It will compute your styles. And if you have optimized layout and paint won't happen, but composite will happen. So using CSS animations, your browser knows that this is my starting point, this is my end point, these are my elements which I are animating, this is my duration, so it can optimize the layers accordingly. But JS animations on every frame, the browser does not know that it's animating right now. So what might trigger is update layer tree. What's update layer tree? It's where the browser thinks that my current split of DOM elements into layers might not be performant. Let me try again. So it computes the layers again. And it can do it on every frame. And this process is proportional to your DOM size. Let me take an example over here. So this is a pull request. It's the contents of the pull request are not that important. It's just a pretty huge component. What I'll do is I'll open my timeline, and I'll hit record, and I'll scroll. Stop. Oh my God, what just happened? Okay, every frame, my event is triggered, and my update layer tree happens. I'm just taking an example of scroll. This can be an animation as well. So what over here is happening is this is my scroll event. Assume that this is your, your render animation frame or something, like every frame you're animating something. So what over here GitHub is doing is for that sticky bar that you see, it is aligning it to the center. And on every scroll event, what it does, it computes the width, computes my elements width, and then divides it by 2, subtracts this thing to compute this area that I need to align it to the center. And on every scroll, what it does, it sets its left. It's a position fixed element, so it's left to some particular value in pixels. So the browser thinks that he's changed something. My layers might not be efficient. Let me run update layer tree. And you see that it took 28.28 milliseconds, a lot more than your 16 milliseconds budget. So you saw that my scrolling was actually quite performant. It was still smooth because GitHub is using passive event listeners. It has started using it. But if this were not passive, you could have actually seen this lag. So a few months ago, before passive event listeners was launched, GitHub over huge PRs was completely unbearable to use on Mac Chrome. I don't know if this bug exists across other Windows Chrome as well. I'm not so sure. So on Firefox, this runs smooth. But on Chrome, this may not be a bug from either side, from Chrome side or from GitHub side. GitHub can say that, at Firefox it runs well, why not on Chrome? Chrome can say that, hey, why are you setting the same value again and again to the style? Why can't you just keep a variable that, the last value was this, and this is my new value, and check that if it's not different, why are you setting it again? So either way, clashes that, which side it's a bug on. You can check this out right now. The link is over here. So also for JS animations, avoid set timeout and set interval for callbacks. What will happen is that you don't know what frame rate to hit. Where your users may be using various devices, and you don't know how performant that device is going to be. So if you overachieve, code for the same frame might run in the same frame, and you might drop some frames. And if your code, if you under hit and you set your frame rate to be low, then you might not be using your user's device to the full potential. So use request animation frame or a user library which does that for you. What it does, it gives you a callback on the next animation frame. We saw this earlier also from yesterday's talk. Okay, next up in the Rail performance model is idle. So what is idle? Idle is the time when after your page has loaded, the user is scanning through your page. During the idle time, you would want to perform your heavy computations during this time before the user has started interacting with your site. So make sure that you do this in blocks of 50 milliseconds before the user begins to interact, so that you are not wasting your time for some future resource. Your user is not waiting on some future resource to use your website, to use your current page. Again, PRPL is Polymer's performance philosophy. What it stands for is push your critical resources, render your initial route, pre-cache your remaining routes, and lazy load your remaining routes. So what essentially during idle time, what you'll be doing is you'll be doing pre-cache and lazy load. There is a new feature which is coming up in Chrome, that is request idle callback. What it'll do, it'll call you when the browser is free. So you don't need to, determine, how do I determine whether, how that the user browser is free. So this is a new spec which is coming up. Facebook and GitHub have started using this. It's currently available only in Chrome, but it's coming soon to other browsers as well. Next up, load. So the guideline set by Rail is to load in 1 second. And in India, 3G connections, that's very difficult for first load. So what you need to do is that you need to aim that at least your repeat users should, for them, the page should load in 1 second. There are a lot of areas where you can optimize your load time. Explaining each one of them is outside the scope of my talk. I'll just talk on one important metric, that is speed index, which is important for perceived performance. So let's take a look at these two examples. Over here we have Gmail, over there we have Amazon. Oh, I need to play this. Crap. So which one felt faster? Obviously Amazon, because as and when the things were ready with Amazon, it started loading it. With Gmail, what happened was that it needed to load everything for your inbox, and then it showed it. So next. So what is speed index? The average time at which visible parts of the page are displayed, expressed in milliseconds and dependent on the size of the viewport. So what speed index? How to measure speed index? What is done is that you take a video of during load time, and you see which pixels represent their accurate state at the end of the payload, frame by frame. So what you do is that you plot the visual completeness of the two of your website on a graph. Okay, over here on x-axis we have time, on y-axis we have visual completeness. So Gmail, you saw that initially some white space was equivalent to in its final stage. So we saw that it was 18% visually complete in less than 1 second, but then it took 11 seconds to reach 90% complete, visuals complete. While Amazon, as soon as the initial stuff was ready, it showed it, and it was 85% in 4.5 seconds, and slowly it loaded the remaining. So what is speed index? Speed index is actually the area above the curve, and the lower the speed index, the better. A speed index less than 1000 is what you should aim for, but it's okay. For repeat users, make sure that it's less than 1000. Speed index depends on network conditions and screen size. So make sure that you are comparing two speed index scores, that you maintain your test conditions. Web page test allows you to do that. I'll just show a quick example. Oh crap, I don't have net. So over here, we ran a web page test for our website, and check it out. I don't have net again, crap. Okay. Sorry. Yeah. Just. It's okay. I have another. I think I had it. Okay, so what happens is when you run web page test on your website, it will show speed index, a metric, and you can I just wanted to show that. I'm at the end of my talk, so it's. So again, the summary. Response, tap to paint in less than 100 milliseconds. Swipe to paint in less than 16 milliseconds to achieve your 60 FPS. Again, animation, each frame in 16 milliseconds. Idle time, use your idle time proactively to schedule your work. Make sure that work gets completed in 15 milliseconds of deferred chunks. Load, make sure that it's ready to use in 1 second, at least for repeat users. Aim for a low speed index. And that's it. Questions?
Hello? Excuse me?
Yes.
Can you show the slide URL? The first slide.
Okay. It's. They are available. They are pinned tweet on my Twitter handle as well, AzizHK110, if that's simpler to write.
Thank you.
Welcome.
Any questions?
Full bouncer or no questions? Okay, I think so. This must be pretty old stuff. Okay.
Hi, nice talk. You need not be sorry for React. It's also JS. Anyway, so my question is: have you tried the purple pattern? What's your opinion about it?
Come again?
Have you tried the purple pattern? What's your opinion
about the PRPL?
Yep.
We are using it, but we are not using Polymer as such. So instead, on Housing Go or PWA, once the page is loaded, our service worker prefetches the other pages, the components for the other pages as well. And for push, the P part, we are not using HTTP push right now, but we are trying for it.
Yeah, but it's not specific to Polymer as such, right? It could.
Yeah, but PRPL, we are using PRPL. Yes.
I was just curious. Thank you.
Hello. You've talked a lot about the technical aspects of creating performant apps. What about the psychological aspect? Have you done any work on like what kinds of animations, what kinds of user interactions make the app appear faster as to actually being faster?
No, I have not done. So essentially, they should look performant. At least you should not have, at a technical endpoint, you should not have jank or sluggishness. but like how your motion should be. I think so. There's Google's material design, which explains in detail how your animation should be, how if you're going from one page to another, make sure that your animations are fluid and they look like as if they are going in that order, and you can follow Google's material design for that.
Okay, thank you.
Do you want me to show you an example of contain? Great job. Nice. Just give me some time. I'll connect to HB. What's the password? Thanks once again. It's okay. Rahul. Phone. Hotspot. Still have time. Still have 10 minutes. It's okay. I have my own hotspot. Yep, it's working. So, wow, nice. So over here we have an unoptimized example. Let me just open timeline. Okay, Command E to record. And okay. Why can't I scroll? Okay, so I'm animating over here. This is an unoptimized example. Let's take a look. So it was not that slow, but just give me a second. Sorry, I can't actually see what's happening over there. Okay, here's the example, termvader.github.io/css-contain. There are two examples, an unoptimized example and an optimized example. You can run a timeline over both of those examples. You will see that the layout process, the time taken for layout does not decrease that much if you have a very fast laptop. But you can see the number of nodes dropping, and you can see the root layout for layout process. It's the div on which you have set your contain, and the number of nodes that need layout, that would drop.
So one of the reasons for using pure.js animation over CSS is interrupting. CSS animations are not interruptible. CSS animations are not interruptible.
No.
So that becomes a huge use case for using pure.js animations. But at the same time, the use cases are not so complex enough that we need a library like React Motion.
Okay.
So how do you go about interruptibility in JS animation? I mean, performantly doing JS animations when you want you want them to be interruptible.
Okay. What you can do is, I guess, just remove the element from DOM on the next animation frame, add it again with the final state. That is one thing that you can use, I guess. Other than that, I'm not so sure of. Cool. Yeah. So that first paint and then run my function. So that gives you 60 FPS.